In this video, we will continue our discussion on how to design a series resonant pulse inverter for wireless power transfer applications. In a previous video, we found that we have 6 unknowns: the required inductance and its ratings, the required capacitance and its current rating, the input decoupling capacitor, and the parameters for the switches, its equivalent on resistance and its current ratings. And in a previous video as well, we found an expression, an equation to find the required inductance L as well as the required capacitance C. And we discussed that in order to find the current rating of the inductor as well as the capacitor and also the maximum current in the switches, we need to essentially find an expression for the current in the series resonant circuit. And to find the current, what we did is we evaluated the equivalent input impedance of the series RLC circuit. And we know that this voltage that's provided by the half bridge is a square waveform, is a square voltage. And so essentially it will consist of a DC component, a fundamental, and a third order harmonic. And since the RLC circuit is basically a bandpass filter with high quality, so it will only select the fundamental component and reject the remaining components. And so the current in the series resonant circuit will be basically the fundamental component of this square voltage, V1, divided by the equivalent input impedance, Z. And in a previous video, we found an expression for the equivalent input impedance of the RLC circuit. And it depends on the characteristic impedance of the RLC circuit, its loaded quality, its resonant frequency, as well as the operating frequency. It varies with the operating frequency of the half bridge. And you can express it in polar form as the magnitude of the impedance and a phase psi, or in Cartesian as real part and imaginary part. And we found that the real part of the equivalent input impedance of the RLC circuit can be expressed as the magnitude of the impedance cosine psi, where cosine psi is given by this expression. And we'll find that if we rearrange the term in this equation, we'll find that the magnitude of Z as a function of R is going to be R divided by cosine psi. Now all we need to do is to find the fundamental component, an expression for the fundamental component in the square voltage that's provided by the half bridge circuit. So first of all, we know that the Fourier series of a square voltage can be expressed as, or it will have a DC component given by half of the supply voltage for the series resonant circuit, given that it's 50% duty square wave. So the high part is 50% of the cycle, the low part is 50% of the cycle. So the DC component or average is going to be VI over 2. And then we have harmonics at 2VI, or the amplitude of this harmonic is proportional to 2VI over pi, or 2 over pi times VI. And then we have the fundamental component, sine omega t, where omega is the radiant frequency or the operating radiant frequency, plus the third harmonic, or 1/3 sine 3 omega t, plus 1 over 5 sine 5 omega t, and so on, the odd harmonics. And so all we're interested in is the fundamental component, because as I mentioned, the RLC circuit behaves as a bandpass filter with high quality, so it will only select the fundamental component of the square voltage, V1. So the fundamental component is given by this expression. So we can say that V1, the fundamental component as a function of time, is going to be 2 times the input supply voltage for the series resonant pulse inverter times sine omega t. And then what we are interested in is to find an expression for the current in the series resonant circuit. And the current, as we know, will be the voltage in the across the series resonant circuit divided by the equivalent input impedance of the series resonant circuit. And so we will find that this will be given by 2Vi over pi times z sine omega t minus ipsi, where ipsi is the phase of the impedance. We can express the impedance as magnitude z e by this expression j ipsi. Okay. Now, if we look at this current in the series resonant circuit, let me rewrite it here. We know that the real part of the equivalent input impedance of the series resonant circuit is given by the magnitude z cosine ipsi. And so we can replace the magnitude z as r divided by cosine ipsi. And so the current in the series resonant circuit is given by 2Vi over pi r times cosine ipsi. And then we have the sine function. So let's see how the magnitude or the amplitude of the current changes with the function ipsi. So two things we mentioned in a previous video. When we looked at the function ipsi versus the normalized operating frequency, we find at resonance, essentially when the operating frequency matches the resonant frequency of the RLC circuit, the phase is going to be 0. On the other hand, for frequencies above resonance, the phase ipsi approaches plus 90 degrees. And for negative frequencies, the phase approaches minus 90 degrees. Okay. And so, essentially, if we look at the amplitude and how it changes with the operating frequency, which it changes the phase ipsi, we have two bounds, pi over 2 and minus pi over 2. And at resonance, ipsi is equal to 0. So essentially, we will find that the current is in phase with the voltage that's generated by the half bridge. Okay, so this is the current, and this is the output voltage of the half bridge, the voltage here, this one. And so cosine psi is going to be 0, and so the amplitude of the current is going to have its peak value given by 2 vi divided by pi times r. Otherwise, the cosine function, the amplitude of the current changes with cosine psi, which looks essentially like this as a cosine function. Okay, so essentially the current decreases as the operating frequency deviates from the resonance frequency, whether going up or going down. It's going to introduce a phase psi, and which lowers or introduces a fraction via cosine psi function. And so essentially the amplitude of the current in the resonance circuit will decrease, and the peak value of the current in the resonance circuit happens when the switching frequency or operating frequency of the half bridge or the switches matches the center frequency or the resonant frequency of the RLC circuit. And so from that we can easily find the current rating for the inductor and the capacitor, so that we can select the right components that can handle that current from a supplier, say DG-Key, Moser, or any other supplier, electronic components supplier. So if we take the amplitude or the peak value of the current in the inductor, it will be 2 vi divided by pi times r. And its RMS rating, since it is a sine function, it will be 1 over square root 2 vi divided by pi r, which is equal to square root 2 vi, the input supply voltage for the series resonant pulse inverter, divided by pi r. And that's basically the maximum current rating required for the inductor RMS current rating, as well as for the capacitor. Now, if we look at the switches don't carry sinusoidal current. It only sees half the function, half the current. So if this is the voltage, this voltage, it's a square voltage that repeats. Here in the first half, S1 is on. In the second half, S2 is going to be on. Now, if we look at the current, at resonance, the current is in phase, psi is equal to 0 at resonance. So when the square voltage essentially matches the resonant frequency of the RLC circuit, we'll find that the current is in phase with the applied voltage. So essentially it's a sine function with 0 phase. And so S1 will only see the first half, and S2 is going to see the other half. So S1 would see the positive half of the sine current in the RLC circuit, while S2 will see the negative half of the RLC circuit. And then it's 0. On the other hand, so since the current in the RLC circuit in the second half is negative, this means it's going from right to left, which goes from the drain terminal to the source terminal. So if we consider the current in S2, the reference direction of the current in S2 is in this direction, from top to down or from drain to source. Essentially, so this means the current going through it is going to be positive from drain to source, although the current in the inductor is negative, right? So this means that the maximum current that the switches S1 will see is going to be 2Vi divided by pi r, because cosine ipsi is 0. So cosine ipsi is 1 because ipsi is 0. And similarly, the maximum current rating that's required from S2 is also given by 2Vi divided by pi r.